Every artificial intelligence data center, every electric vehicle, and every node of global telecommunications relies on a physical foundation smaller than a biological cell. To keep these systems running, we have to build microscopic pathways that route electrical signals at the speed of light. The engineering discipline that makes this possible is very large-scale integration, or VLSI. It is the exact science of packing billions of microscopic transistors, tiny electrical switches, onto a single piece of silicon. 70 years ago, achieving a fraction of this computing power required room-sized banks of fragile vacuum tubes and mechanical relays. Today, we manufacture billions of these computational switches on flat squares of plastic. We construct them with atomic precision, millions of times over, where a single geometric mistake can render the entire processor useless. We are building a dense, three-dimensional metropolis, where the architecture must be perfect at the scale of individual atoms to withstand the crushing laws of microscopic physics. The process begins with jagged chunks of raw polycrystalline silicon. We melt these nuggets down in a vacuum at over 1400 degrees Celsius and pull them into a single ultra-pure cylindrical ingot. In step 1, wafer preparation, diamond-coated wire saws slice that silicon ingot into ultra-thin discs known as wafers. But slicing leaves microscopic grooves and lattice damage on the surface. This schematic shows the mechanical process required to fix that damage. It illustrates the pressure and chemical slurry applied between a wafer holder and a polishing pad in a step known as chemical-mechanical polishing. The alkaline slurry and abrasive pads grind the silicon down, erasing the saw marks. A flawless, mirror-like finish is a strict physical prerequisite. If the base layer is uneven by even a few nanometers, every architectural layer stacked on top of it will be structurally compromised. With a perfectly flat base, we move to step 2. Deposition. Here, a thin, uniform layer of insulating or conducting material smoothly forms directly onto the blank silicon wafer. Next is step 3, photolithography. We coat that newly deposited material with a liquid, light-sensitive organic polymer called photoresist. We then project extreme ultraviolet light through a patterned mask. When the 13.5 nanometer light strikes the photoresist, it triggers a chemical reaction that hardens specific geometric patterns into the polymer, creating a nanoscale blueprint. This sets up step 4, etching. We introduce chemical plasmas that eat away any material not protected by the hardened resist. When the process finishes, permanent, three-dimensional physical structures remain. We repeat steps 2, 3, and 4 dozens of times. Deposition, lithography, and etching loop continuously, stacking layer upon layer, to build the chip upward into a complex physical grid. At this scale, light and chemistry provide the only exact mechanisms capable of carving structures smaller than a biological virus. Even with a perfect physical structure, pure silicon is an electrical insulator. To make it functional, we have to change its chemical identity. This slide from an engineering course defines the solution: ion implantation. By ionizing dopant gases and accelerating them through a vacuum, we fire high-energy ions straight into the silicon lattice. These charts plot the physics of that collision, showing ion penetration depth and standard deviation against the implant energy for different elements. By strictly controlling the acceleration energy, we dictate exactly how deep the ions penetrate, creating the specific positive and negative regions a transistor needs to switch current on and off. This high-energy physical bombardment is the exact mechanism that transforms a passive piece of carved rock into an active, logic-driven electrical switch. Now those switches need to communicate. In step 6, metallization, we deposit stacked layers of microscopic intercepting copper highways. This wiring connects billions of isolated transistors into a single cohesive network. In step 7, testing and slicing, robotic probes check the fully patterned wafer for electrical flaws. A diamond saw then cuts the silicon into hundreds of individual chips, known as dies. Finally, in step 8, packaging, the fragile silicon die is enclosed in a protective housing and wired to external metal pins. Packaging provides the critical bridge that allows a delicate, atomic-scale environment to physically plug into a motherboard and survive the temperature and moisture of the macro-sized human world. Over several weeks, a raw ingot is sliced, printed, bombarded, and wired until it becomes the brain of a computer. The industry is now pushing into the angstrom era, aiming to shrink transistors below 2 nanometers in width. At this microscopic scale, engineers battle quantum stochastic effects. When a single feature is only a few atoms wide, a small handful of random stray electrons from a light burst can ruin the chemical reaction and short-circuit the entire chip. After weeks of bombardment and light carving, a once inert rock now manages trillions of operations every second. It is a physical environment where we have successfully forced the chaos of the atomic world into a predictable, logical grid.